Okay, energy spacing, do you have any question? Basically, this is simple. This I just ask you to, I just ask you to plot, right, the energy spacing of a potential well when you have A, then you have this spacing, right? And that goes with h bar square, I mean, for each level, divided by 2m pi over A square n square. Make sense? We discussed this in the class, right? Particularly the last lecture last week, right? We gave all the equation. I actually gave all this in the last lecture on Wednesday. Yeah. So nothing special. We just plot E1 minus E0 as a function of A, right? I asked you to step from 0.5 nanometer to 10 nanometer. And at the same time, I want you to see how the thermal energy change if we assume it is at the temperature with the how the temperature change if we assume the energy is 1/10 of the spacing, right? Again, if I have a thermal energy is only 1/10 of this spacing, then I'm pretty sure that it will occupy only the bottom. If the thermal energy is large, due to Fermi-Dirac distribution, I can have some of them occupy on the top, right? And that's why I asked you to plot 1/10 of that one. So this one is easy. The point is, do you understand the question? Any questions? Why we're doing this? Yeah. Yeah, so here is something I did not do it well. You cannot have 0, right, for this equation. So what I mean is the first level and second level. Some of you ask me, then I tell them it's not clear. Some of you did not ask me. You either see problem or you just don't care, right? So I did not announce it. So I'm wrong. Here I actually changed it already, but here I should make it to E2 minus E1. But doesn't matter because in the class I also told you already. If you remember, if you did watch the video from last class, for some paper they use E1 minus E0, right? So, but doesn't matter. If you say, wow, you confuse me, you make me think that this is 1 square minus 0 square, fine. Tell me when I grade it, I will give you full score. That doesn't matter. Right? But the point is, you should understand there's some problem, right? If you understand why I asked you this question, because you should know that no carrier can occupy at the bottom level. There's no point to ask you what is E1 minus E0. Yeah, but yes, if you feel that that's my problem, let me know. I will give you full score in the assignment. Yeah.
For the temperature one, you want to spot spacing or the actual?
I want you to plot about spacing in A. Well, what do you do?
Spacing.
It means that if you have a quantum well which is 10 nanometer and you still want to see the quantum effect, you better have a temperature that is below 100 Kelvin, right? But if your quantum well is small enough, let's say up to 5 nanometer, you will already see the quantum effect at room temperature. Yeah. Okay? I think I say that, right? Not explicitly. Show your equation. Plot on the same graph, the equivalent temperature, right? Same graph.
Different Y.
But plot on the same graph, right? X-axis means need to be the same and Y. I mean, you can combine to the left, but you should have the right number. You should say this is EV. Plotting is also very important, right? But don't worry, I'm going to grade very linearly because I'm lazy. That's it. Okay? I really, as long as you work on that, I will give you high grade, right? So don't worry about that. But the main point is I want to challenge you, right? If you go to interview, you should know what to plot, even it's not clear. I say plot on the same graph. Or you should ask, right? You should not, if you think there's a problem, you should have emailed me to ask. But if you do it in the last minute, then I cannot help you. Okay, this is important. Okay, I always give you hint. Now this one, what does it do? It say a transistor. What does it mean, right? So I have a transistor here. A transistor. I'm doing the measurement. So this is source, this is drain, and it's running at 1 volt and 1 milliampere. And what is the power of a circuit? How do you find the power of a circuit if I give you current and voltage? Yeah, IV. This is very simple, but I bet some of you forgot or are not that familiar with. And you should know that. Power is just the total current times the peak, the terminal voltage. You should know that. Huh? I gave you, yeah. But I may not give you in the midterm. I'm very nice, I told you. I'm a very nice professor. Okay? But you should, what do I say? I mean, this, you should know this, right, in the phone interview. I mean, if I ask someone this and you don't know that, how can I hire you as a circuit designer? Right? You don't need to go to details, but you need to show people you know something. And then you can Google or Wikipedia. Right? If you completely blank, then they don't want you. Right? So now, you are right. I gave you already. If I don't give you, then you know how to do, right? I times V. Now, so what this question is asking about, it says this transistor is sitting on a silicon slab. And it's difficult to understand, but no one asked me. So I assume you all understand. It has a length of 1 micron. And the area, right? So this is not true. I make it really straight. You won't get such a bad self-heating. But here area is 100 nanometer times 100 nanometer. Is this okay? That is the problem statement. I have a heater here. Basically, transistor is just a heater in this case. I'm heating up with a transistor, 1 millivolt. And then I only have this lab connecting all the way, and the ambient temperature. Here I did not say ambient, I say ambient, right? Just here I touch the chiller. It can be at 5 Kelvin or 200 Kelvin, whatever, right? If I say ambient temperature at 3 Kelvin means that is 3 Kelvin or 300, and then 300 is 300 Kelvin. And I'm asking you, what is the temperature at this point at steady state? So I keep heating it up, then of course, then the heat need to dissipate, right? And I already spent a lecture talk about how it's related to the, analogy to the Ohm's law, right? Ohm's law, we have what? V times conductance equals to, no, right? Electric field times conductance equal to J, right? So, but you don't need to memorize this because you can have cheat sheet, right? So, delta T. Now, the reason you have temperature flow is because here you have a T. Here is T naught equal to 200. This is the delta T, T minus T naught. It causes the heat to flow from top to bottom, right? And that is and how much heat do you dissipate? Whatever you generate need to dissipate. Otherwise, you will keep increasing the temperature. Make sense? So the heat flow must be the power that you generated. But then, related to what? To the thermal conductivity, right? The thermal conductivity, if I were you, I will write it in the cheat sheet, right? So this one is sigma, not delta. Okay, sigma, but doesn't matter. So, what do I want to say? So here, yeah, of course, this thermal conductivity, but here I try to put resistivity here. So I can also say this is divided by the resistivity, right, times L divided by A. It's easy to memorize. The longer the slab, then you have a larger resistivity, right? Because it's more difficult to dissipate the heat. And then larger area, you have smaller one. So if you can memorize this, is good. If you cannot, then just what? Write in the cheat sheet. Do you get it? And maybe I write something wrong, but anyway, let's look at this. Delta T divided by the thermal resistance equal to the power. And what is the thermal resistance? It's the thermal resistivity times L divided by A. And then thermal resistance is 1 over the thermal conductivity. Then just plug in the equation, right? Go home and try again. Make sure that you understand. Then you get the answer. And what do I want to say? I ask you to refer, but this is important, right? I ask you to refer to the figure in the slide. And then you approximately get what you get, right? It doesn't matter if you give me 6 or even 10, I'm not going to deduct the score, right? But I tell you how I caught student cheating. It was that I gave them a graph and they give me exactly the same number up to 10th digit. And I told them that it's impossible. You get the 10th digit by reading the graph, right? The probability is very... There was one year I caught one cheating. That was during COVID. They live in the same house. And then I found that they read the graph, all get the up to 7-digit accuracy, same as each other. They reading the graph. And I say that this is a great proof that you are cheating. Just kidding. But anyway, right? It doesn't matter. So one thing I want to remind you, WCK, you need to make sure that you have the right unit. How do I convert? Let's say 1 volt per cm per Kelvin. How do I convert it to 1 volt per meter per Kelvin?
10 to the minus 10 to the plus 2.
Now, think about this. I have something per cm. Then what do I have per meter? 100. So you need to multiply this by 100. Is this clear? So if I have a question like this, the difficulty is to convert to the right SI unit, which I want you to do it yourself. I gave you hints already, yeah.
Yes, I was using the equation I think you had in your slide. Plus 5, 8. I think it comes up to the same.
Yeah, they're all the same. Yeah, double check. Yeah, it's a good time to learn. Yeah. Okay, so please make sure that you understand the stuff. Now then, here I ask you to do the simulation for the 45 nanometer and FinFET, right? Some of you will say, don't know how to explain. I don't know either. For example, this is the output resistance, right? And we know that the RO should reduce with temperature. This is correct, right? But then now it jumps up like this. Do you know why? Any other answer? He's right. No one dare to say that, right? Because you thought it's authority, right? But yeah, we gave you the wrong model because those models are not calibrated to 4 Kelvin. Usually, and this is a generic model. If you get a model from TSMC, they will guarantee, for example, I don't know, negative 50 degrees C or something, right? Yeah. It keep degrading, yes. Yeah, decreasing. GM increase and RL decrease, and somehow they compensate each other. What makes RL decrease is a little bit complicated because RL is related to the channel length modulation. And then it changed the V set. Yeah, I cannot explain on top of my head, but it's related to the saturation velocity, all these things. Yeah. So I mean, if you know you're doing the right thing, dare to challenge the authority, right? But I did not ask you. Did I ask you to explain? I did, yeah. But again, as long as you try to write something, no problem. Okay. Now, again, very important, right? Question 4. Another hint. Okay, so this is a curve, right? I mentioned subtraction slope for how many times? 1 billion times, maybe. So if you still don't study, not my problem again, right? So don't put that in my evaluation. So what is subtraction slope? Very good. Right. So again, what curve is this? This is IDVG, right? Is this in log scale or linear scale? Log scale, right? Because you see that it increased by 10 times every tick, right? If I plot it in linear scale, what do you see? Maybe something like this, right? This is almost 0. Looks like 0, but maybe 1e minus 6 is 1,000th of what I'm seeing. Of course, it's basically 0, right? So you should be able to do that. And as he said, what is the subtraction slope? It's like, I just pick a point. For example, I say use the 1e minus 9 and 1e minus 7 region to calculate the subtraction slope. Then I want to, so what? How many decades do I have here? 2, okay? Because minus 9 to minus 8 is 1 decade. Minus 8 to minus 7 is 2 decades. Then my question is, how much voltage do I need to increase this 2 decades? Then you just count it, right? So pretty almost like, because this is shifted a little bit, this shifted a little bit, so it's just like 1, 2, 3, about 3 units. So that is about 150 milli EV, 0.15 volts. Is that okay? Because this is 0.5 and I have 10 ticks, right? Here I put 160, maybe because I plot this graph myself, maybe I probe it, but doesn't matter. You give me 150, actually it's more accurate than 160 in some sense. I'm sorry, should be millivolt. Yeah, millivolt. Okay, is that okay? Then how many, what is the subtraction slope? Divided by 2, because now it's 150 millivolt per 2 decade, right? So it is 75 millivolt per decade. That is the subtraction slope. You need to reduce to this. Right? This is a big hint. If you don't know this, you better study. Okay? 80 millivolt per decade. In my case, because I start with 60 millivolt per 2 decades. Okay, that is the subtraction slope. And then, of course, you would want to know, for example, the equation, right? You know the subtraction slope is equal to KT over Q log 10 times N. N is the ideality factor. That's why I say if N equal to 1, based on this, what is the operating temperature, right? If this is 1, then you're basically saying that this term give me, I go back to my 80, right? Give me 80, right? So I use the proportional factor. I know that for 300 Kelvin, what is the ideal subtraction slope for 300? 60. This one you need to memorize. If you don't, then you better memorize what's KT and Q, right? For those who are scared, put K and Q in your cheat sheet, right? Watch out for the number, right? So of course I know that the temperature I have divided for 300 must be equals to 80 divided by 60, because, sorry, I go back to 80 here, because I assume it's 80 millivolt per decade. Okay, so 80 instead of 60, then my temperature divided by 300 must be 80 divided by 60, right? So this is 400 Kelvin. So I can use this to measure the temperature in some sense, if I know the N, right? Now I say, actually, it is not 400 Kelvin, it is 300 Kelvin. Then I ask you to explain. Then why I got 80? Because my N is not equal to 1. my N is equal to 1 plus C depletion divided by C ox, right? So from there, you know the C depletion divided by C ox is 0.33. Yeah. And then another question is, well, my N is actually 1, right? Then, but I still get this. What can be the possibility? Then that can be due to short channel effect because you have the drain control. The equation given here is an ideal 1D case. Okay? So just as an example, right? If this is a log scale, if I have something like this, what is the subtraction slope of this guy? Huh? Yeah? Who agree with who? He says 0, you say infinity. Now, by definition, what is subtraction slope again? Ask yourself. In order to increase 10 decade, how much voltage you need to shift, right? So here, to increase 1 decade, not 10 decade, how much voltage I need to shift? 0. So you both are right. Now you can challenge me, say, oh, this is not subtraction, this is subtraction swing, like what the reviewer want to say. But you all understand, very good, right? So, you know something, right? So don't be unhappy if you are wrong in the interview. Just say, yeah, I did not sleep well because of daylight saving. But they know that you know something, right? So keep adjusting. Good. Then we talk about the incomplete ionization. Here I just ask you to plug in the equation. I'm not going to repeat. Okay? Maybe you can put in your cheat sheet. King effect, another important one. Okay, so what is King effect? ID, VD, right? What do you get? I have different VG. This is a normal curve, normal ID, VD curve. And what happens when I have King effect? There's a jump, very good. So I will have something like this. Right? Why I have this jump? For about MOSFET. Not partiality, I'm talking about MOSFET. Okay, let's learn from him. So he said, let's do it step by step. So he said, this is the MOSFET. It is 0, and maybe this is 2 volt. And then we increase the VD from 0 to, let's say, 5 volt, right? And then at the beginning, we have a normal curve, and then suddenly it goes up. Then can you continue your story? Okay, no, just now you first said there's an impact ionization. Why there's an impact ionization? It's a PN junction here. Which PN junction caused the impact ionization? He said between the drain and the substrate. And because this is the only one that you have a big potential difference, right? This is a PN junction. Remember how do you do it? This is PN junction. P at the bottom, Fermi level, N, right? This is 0, this is 5. Are you able to draw this? Do you understand? Make sense? I already emphasized in the SRK dial, right? This is my 1001 time talking about this. So you're supposed not going to have currents because yes, electron will go here, hole will go here, but I don't have much electron, I don't have much hole. Reverse bias. But then he said there's impact ionization because I still have finite amount of electron. Okay, so this electron will come here, and then because of this high energy, it might actually release another electron hole pair, create another electron hole pair by releasing its energy. right? Or in classical picture, just someone comes in and then knock one of you down, and then you have an empty chair, and then you walk around as an electron. And then under this high electric field, this hole will come here, then you might also create another electron hole pair, right? That's like avalanche. And that's why you have impact ionization. Now, when you have impact ionization, that means originally you don't have current, but now you have current going from the drain to source, right? High voltage to low voltage. And then what do you want to say? And then because you have a finite resistance here, then because you have current, then this is no longer at 0 bias. It might be at 0.2 volt due to the potential difference. And when it's 0.2 volt, then you reduce the threshold voltage because the substrate is forward bias, right? And that's why your current goes up. So why I don't have this at low VD again? Why it only comes up at high VD? Yeah, very few impact ionization or no impact ionization, right? So you don't have current, okay? And this is a cryogenic class, right? If I ask this question, my next question is what happens when you go to low temperature? There are many things, right? So he said, substrate freeze out, then you will cause larger resistance. Then you might have more King effect, earlier King effect, right? Because more potential drop. But plus you have more impact ionization because you don't lose energy to photon. You keep accumulating and eventually you have enough energy. If it is very hot, you keep losing. You just keep going down like this. You never have enough energy to create impact ionization. But what about the carrier concentration here? If it's in an absolute zero, then I even don't have electron to initiate this impact ionization, right? I think I'm right? Yeah, but however, so it's all up to you to argue. Right? It's just need to give something reasonable, right? And indeed, you cannot just say a 0 Kelvin because we have, in reality, we have cosmic radiation. The neutron, alpha particle keep hitting your device. So just one of them can create this impact ionization. So it won't be dominated by this source. Okay?
I mean, a radiation.
Yeah, I mean the alpha particle, neutron particle, they hit your silicon, they create electron hole pair. So you don't need this initial source from the source entry. Okay, yeah, or night, yes. Okay, so I think that's all I want to review. I gave you a lot of hints already, right? That make me feel happy and I can grade it more strictly. So just study and email me if you have questions, okay?